Assalamu alaikum students. Today we move from the force description of motion to the energy description of a particle's motion. In the previous lectures we focused on forces and equations of motion. Now we will see that many mechanical problems can be understood in a different and often a more simpler way by describing its energy. This becomes important in systems where some forces are not easy to calculate directly. These are often called the constraint forces, which arises because the motions are restricted, or you can say bounded, by strings, pulleys, rods and surfaces. In this lecture we will study how potential energy helps us describing such kind of motions, equilibrium and stability. And at the end we will conclude by discussing where Newtonian mechanics itself begins to fail. In this lecture our goal is to understand why the energy description is useful in mechanics. We will study conservative forces, potential energy and the total mechanical energy. Then we will use the potential energy curves to understand allowed motion, turning points, bounded and unbounded motion and equilibrium along with its stability. After that we will discuss why constraint forces do not appear explicitly in energy equations even though they are present physically. And finally we will examine the limitations of Newtonian mechanics. In this course we are following the book by Marians and Totten. Let us begin with the basic equation. Why do we need an energy description when Newton's second law already gives us the motion? In the force description we write mx double dot equals f of x in the 1D case and then solve for the motion. This method is fundamental and exact, but sometimes it becomes difficult because the forces may be complicated, partly unknown or tied to the geometry of the system. And that is where the energy methods become useful. In many bounded systems, motion is not completely free. A particle may be forced to move on a surface or along a string, or it can be constrained to move on a track or in a pulley arrangements. Now these restrictions generate what we call constraint forces. How we can define it? A constraint force is simply a force that ensures that the object follows the allowed path or condition of motion. For example, the normal reaction of a surface, the tension in a string, or we can say the force from a rod, or all constraint force is example. Now the important point is that in many situations these constraint forces do not work because they act perpendicular to the actual displacement. Since the energy method is based on work and energy, those forces naturally disappear from the energy equations. So instead of solving many vector force components, we often solve one scalar equation involving energy, and that is why the mathematics becomes simpler. Now we introduce the idea of a conservative force. A conservative force is the one for which we can define a potential energy function u of x, that is energy as a function of position. The force is related to the potential by f of x equals minus du by dx, that is gradient of the potential. The minus sign tells us that the force acts in the direction of decreasing potential energy. That is, naturally the system is pushed towards lowering the potential energy. Now, for such a system, the kinetic energy is defined as half mv square, and the total mechanical energy is the sum of kinetic energy and the potential energy. Now, if only conservative forces act, then the total mechanical energy remains constant. Now, from the figure, it is clear that a potential energy curve shaped like a bowl with a horizontal line representing the total energy, the vertical separation between the energy line and the potential curve represents kinetic energy. So, at any point, part of the total energy is stored as a potential energy and the rest appears as kinetic energy. So, this shows how energy is shared during the motion. Now, based on the previous slide, here we are discussing the one-dimensional motion under a conservative force such that the total mechanical energy can be expressed as the kinetic energy plus the potential energy. If we rearrange this, we can get half mv square equals E minus u of x, that is the difference of total energy and the potential energy. And from there, one can calculate the speed in terms of position. So, instead of first finding acceleration and then integrating repeatedly, we can often understand the motion directly from the energy. The plus and minus signs represent motion in two possible directions. The square root also tells us an important physical condition, that is the E minus u of x should always be equal or greater than 0. Because v square cannot be negative, now that means motion is only possible where the total energy is greater than or equal to the potential energy. And that is why we highlighted that statement here. The potential energy curve itself tells us where the particle can and cannot go. The integral written below gives time in terms of position. It is the formal solution for the motion. Even if we do not evaluate the integral fully, it shows that once we know the potential energy, we have in principle solved the problem. Now, that small sketch shown on the right with the ball in a potential well gives the concept here, that the particle moves only in the allowed region of the well. Now, this is important conceptually. The potential energy curve is not just a graph, it is a map of the motion. At every position x, the kinetic energy can be described as E minus u of x, that is total energy minus the potential energy. So, if the total energy is greater than the potential energy, then for those points t is greater than 0, that is particle can move there. On the other hand, if the total energy is equal to the potential energy at a given point, then we get t equals 0 for such case, so the speed becomes 0. If so, that is a turning point. If the total energy is smaller than the potential energy, then t is less than 0, which is impossible physically, so the particle cannot be in that region. Now, look this figure carefully. The curve is u of x. that is potential energy as a function of position. The horizontal lines represent different possible values of the total energy E. Whenever the horizontal energy line cuts the potential energy, those intersection points are special. They are places where kinetic energy becomes zero. In another word, we can call it turning points. So the energy line act like a reference line or reference level. Below that line, the particle can move. Where the curve rises above the energy line, that region becomes inaccessible, and that is why potential energy diagrams are useful. By just looking at the graph, one can say whether the particle is trapped, free, oscillating, or escaping. Now here we use the potential curve to classify motion. Bounded motion occurs when a particle is trapped between two turning points, as discussed on the previous slide. At both ends, the conditions E equals u of x holds. So the speed becomes zero there. The particle cannot cross beyond those points because that would require negative kinetic energy, and therefore it reverses direction and move back. That is oscillatory motion. Unbounded motion occurs when the particle is not trapped and can continue to very large distances, possibly to infinity. In that case, the energy level is such that the particle is not confined between two barriers. In the figure, some energy levels intersect the potential curve in two places, creating a confined region that corresponds to bounded motion. A higher energy level may allow the particle to move far away without being trapped. That corresponds to the unbounded motion. Now this is important because it shows that we can predict the nature of motion without solving the differential equations of motion directly. We only need to compare the energy level with the shape of the potential. In the energy description of motion, one of the important concepts is the equilibrium point. A point of equilibrium is where the net force vanishes. That is, F as a function of x naught equals 0, where this x naught represents an equilibrium point. Since forces can be described in terms of gradient of the potential, so the equilibrium condition can also be described through the potential defined at x naught. That is the equilibrium point. So equilibrium occurs when the slope of the potential energy curve is 0. Graphically, that means the tangent to the curve is horizontal. This is important because it connects a force and the geometry. If the slope is non-zero, then there is a force pushing the particle one way or the other. On the other hand, if the slope is 0, the force vanishes, so the particle can stay at rest there. Now from the figure one can say that any local maximum or local minimum of the potential corresponds to equilibrium. Because at both locations the tangent is horizontal, but not every equilibrium is stable, means what happens after a small disturbance depends on stability, which we will study on the next slide. To understand stability, we expand the potential near an equilibrium point using a Taylor series, that is u of x expanded around an equilibrium point. For simplicity, here we have taken the equilibrium point x naught equals 0, such that the equilibrium condition holds du by dx at the equilibrium point 0 equals 0. So the linear term disappears. Then near equilibrium, the dominant term is the term proportional to the second derivative of the potential defined at the equilibrium point. Now the sign of the second derivative becomes decisive. For example, if the second derivative of the potential at the equilibrium point taken as x naught equals 0 here, if that is positive, then the potential has a local minimum, that is a stable equilibrium. If the particle is displaced slightly, the potential rises and the force tends to pull that object back towards the equilibrium position. On the other hand, if the second derivative of the potential at the equilibrium point is negative, then the potential has a local maximum, that is an unstable equilibrium. That is, a small displacement causes the particle to move further away instead of returning. The important point is that a minimum of u is like a ball in a bowl, while a maximum of u is like a ball balanced on top of a hill. One returns after a small displacement, the other moves away. Now the constraint forces and its role in the energy descriptions of motion. A constraint means that the motion is restricted. The object is not free to move in every direction. For example, a block on an inclined plane must move along the plane. A pendulum bob must move along the circular arc, and a particle on a track must stay on the track. Now, the forces that enforce these restrictions are called constraint forces. For example, tension in a string, normal reaction from a surface, force of a rod, contact force from a track, and tension forces in pulleys. Now, why do these forces often disappear in energy equations? Because work depends on a force in the direction of displacement. Mathematically, it can be described through the dot product. Now, if the constraint force is perpendicular to the actual displacement, then the dot product is 0. That means the constraint force may be present physically and may strongly affect the direction of motion, but it does not transfer energy into or out of the system. Now, from the figure, in the inclined plane, the normal force is perpendicular to the displacement along the plane, so it does no work. On the pendulum figure, tension acts along the string while the bob moves tangentially along the arc. Again, tension is perpendicular to motion, so it does no work. And that is why energy method is handy in such kind of constraint system, because it allows us to ignore many unknown constraint forces and focus only on the forces that do work and change the mechanical energy. Now we apply the idea to a pulley system. This is a nice example, because if we use force analysis directly, the system can become messy due to multiple tensions and geometrical relations. The figure shows a string passing over pulleys and supporting masses m1 and m2. Because the string has fixed length, the position of the masses cannot vary independently. That is the constraint of the system. So the geometry itself connects the variable. The potential energy can be expressed as in terms of two heights x1 and x2 with the constant c from a reference line AB. The negative sign appears because the coordinates are chosen downward in the diagram. So moving downward lowers gravitational potential in the chosen convention. The important idea is that instead of calculating all tension explicitly, we use the geometry of the string to express one coordinate in terms of the other. Then the potential energy becomes a function of only one independent coordinate. Now that is the real strength of this energy method. The tension in the pulleys are constraint forces. They maintain the connection imposed by the string, but we do not need to calculate each one in detail. Geometry plus potential energy is enough for describing this motion. From the figure, the fixed string length creates constraint, and that is what reduces the problem to one variable. Now we move towards the solution of the problem. First, for equilibrium, we set the first derivative of the potential equal to 0, that is differentiating u with respect to x1 and equating it to 0 will give us the expression for the equilibrium point. Now there we see an important condition, that is 4m1 square should be greater than m2 square. That is, a real equilibrium exists only if this relation between masses is satisfied. So equilibrium is not guaranteed, it depends on system parameters. For the stability, we examine the second derivative, that is obtaining the second derivative of the potential with respect to x1 at the equilibrium point will give us this expression. Now since after holding that condition 4m1 square greater than m2 square will give us a positive second derivative. So the important point is that first derivative 0 gives equilibrium and second derivative sine gives stability. Again this was done without solving a complicated set of force equation with multiple tension. Up to this point we have used Newtonian mechanics confidently. Now we ask, does it work everywhere? The answer is no. At microscopic scales such as electrons, photons and atoms, exact simultaneous measurement of position and momentum is not possible. Now this idea is expressed by the Heisenberg uncertainty principle, where this delta x is uncertainty in position and delta p is uncertainty in momentum. The symbol h cut is the reduced Planck's constant. Newtonian mechanics assumes that a particle has a precisely known position and precisely known momentum at the same time. This assumption works well for macroscopic bodies such as cars, balls and planets, but for microscopic particles this classical picture breaks down. The figure on the slide nicely contrasts ordinary macroscopic motion with microscopic particles. So the message is not that Newtonian mechanics is wrong everywhere, rather it is excellent approximation in the macroscopic world, but not fundamental at atomic and subatomic scales. Now we come to another limitation, the very high speeds. Newtonian mechanics assumes absolute time, meaning time is the same for all observers. It also works under the ordinary low speed assumptions where relativistic effects are negligible. But signals do not propagate instantly. There is a finite maximum speed in nature, the speed of light. Now, when speeds become comparable to c, Newtonian mechanics is no longer accurate, then special relativity is required. So, for slow everyday motion, classical mechanics is excellent, but for particles moving near the speed of light, concepts like time, length, momentum, and energy must be revised. The third limitation is practical rather than fundamental. Even when Newtonian mechanics is valid in principle, it may become impossible to use directly for a large number of particles. For a few particles, Newton's law can be written down and solved, but for enormous systems such as gases, fluids, solids with huge number of molecules or thermodynamic systems, tracking every particle individually is impossible, and that is why statistical mechanics was developed. Instead of following each particles, we describe average properties such as pressure, temperature and density. So the important point is that Newtonian mechanics remains foundational, but different physical regimes require different descriptions. For example, quantum mechanics for microscopic systems, relativity for high speed systems, and statistical mechanics for systems with huge number of particles. In this lecture, we saw that the energy description is an alternative and powerful way of studying motion. For conservative systems, the total energy is the sum of kinetic energy and potential energy, and that remains constant. The potential energy curve helps us identify allowed and forbidden regions, turning points, bounded motions, unbounded motion, equilibrium and stability. We also learned an important physical reason why the energy method is so efficient in many bounded systems. Constraint forces often do not work. Because of that, they disappear naturally from the energy equations, even though they present physically and still shape the motion. Finally, we saw that Newtonian mechanics has limits. It is highly successful for ordinary macroscopic motion, but it becomes inadequate at microscopic scales, relativistic speeds, and in highly complex many particle systems. Now the assignment part. In question 1, you need to derive the one-dimensional energy relation and interpret the condition as shown E minus U of x greater than or equal to 0. This will make you understand why motion is only possible in the allowed region. In question number 2, use the potential energy curve to explain allowed region, forbidden region, turning points, bounded and unbounded motion. In question 3, you are asked to show that equilibrium in the energy description is given by first derivative of the potential and then use the second derivative of the potential to distinguish between stable and unstable equilibrium. Question 4 is based on pulley systems and question 5 is on the limitations of Newtonian mechanics. And that's it. Thank you very much.